Why does ray tracing make your graphics card cry harder than an anime fan on prom night? I'm not sorry at all for making this lame joke. Anyways, this video is about ray tracing, why it's such a big deal right now, and why it basically commits murder onto your GPU. For this, I'll first explain the current rendering paradigm used, Rasterization. But before I do that, make sure to subscribe to this channel and click on the notification bell to avoid missing out on any future videos of great value. Without further ado, let's get right into it.
The basic principle of rasterization is the following. When you look at a scene with your game camera, each object is drawn on the screen one after the other. Each object appears on certain points on the screen and is then converted to pixels. These pixels are then stored as an image, which is known as the frame buffer. Once all objects have been drawn in the scene, the frame buffer is then sent to the display and the rendering of a frame is complete. This process works but is severely limited when it comes to things such as lighting, shadows, transparency, and other potential effects. A lot of tricks are used to accomplish these. The big advantage of rasterization, however, is that it is very performant in displaying a 3D world, which is why it is used for real-time applications such as video games today. One more relevant piece of information here is how many objects or passes per pixel have to be used when mapping a 3D world to a 2D image, such as what is done when playing a game on a typical display. Different objects could end up taking up the same pixel. In rasterization, the object that is closest to the camera is the one that will then actually be used for the displayed pixel. If you, however, rendered an object further away first, and then an object closer to the camera, the same pixel would be considered a second time. There are smart techniques that allow this effect to be mitigated somewhat. In total, we end up having a small, important detail that we need to be aware of here. In rasterization, we usually don't need to evaluate a single pixel more than once. Let's repeat this, just one evaluation per pixel. With this detail known, we can head on over to ray tracing.
You know what, I actually cancelled this video because I'm working on a bigger project right now that should be out next week or next Tuesday. And I wanted some more time with that.
But because I wanted to start having a proper upload schedule, I decided it would be a good idea to quickly make and release this video too. And by the way, I have a question for you.
I put in a poll of your favorite chip manufacturer, Intel, Nvidia or AMD. So tell me which one you prefer. The correct answer is of course AMD, but you're entitled to your own opinion. Anyways, let's get back to the ray tracing.
Instead of drawing each object one after the other on the screen, we shoot rays from the camera into the direction of each pixel. This gives us the first issue. Detecting collision isn't an easy task and requires more calculations than simply drawing something on the screen. Nevertheless, this is still achievable, so let's continue. We also still use only one ray per pixel, so that isn't a problem compared to rasterization with its one draw per pixel approach. However, once we hit an object, the fun really starts. We not only need to take the color of the object at that point, but we also need to consider lighting. Another ray has to be cast from the pixel to every single source of light to observe each light source's contribution to the overall lighting. This already multiplies the complexity of the computation with a number of light sources on the screen. Anyhow, this is still not that big of a deal. A very similar approach has to be done in rasterization, and the trick here is to simply limit the number of considered light sources in the scene. For example, the illumination of streetlights in video games is usually only considered in the direct vicinity of the streetlight. This same trick should once again be usable with ray tracing, so this is once again not such a big deal either. So where does the kicker lie? Why is ray tracing so expensive? Well, take another look at Nvidia's initial presentation. Their sole focus in this technique lied in the implementation of reflections. Reflections are the limiting factor of the rasterization techniques. Any object that appears in a reflection has to have been rendered on the screen somewhat beforehand, aka using screen space reflections. This is of course physically inaccurate, as you are able to use mirrors by looking around corners in real life. So another technique used in games was to instead render an object twice, once inverted and its color slightly changed to mimic a reflection. Reflections are thus the key reason on why we want to move into ray tracing. So, reflections are now giving us yet another ray that we need to trace, but do you think that will remain this easy? If we happen to render a scene with only mirrors in it, then yeah, it would be. The laws of physics unfortunately don't make this so easy for us for two reasons. Partial and diffuse reflections exist. Mirrors are perfect reflectors. If you shoot light at them, this light will come back at a distinct given angle in all cases. But that isn't true for imperfect reflectors, basically everything else. Partial reflections are still quite easy to handle. It just means that a reflection is reflected further. Alas, we just need to cast another ray for each re-reflection. But diffuse reflections are the issue here. Any typical surface doesn't reflect light into one direction only. The incoming light is split up and reflects into a small area surrounding the point where a perfect reflection would reflect to. What this means for ray tracing is that to get a correct image, we would have to cast hundreds, if not thousands of rays into a single pixel to be able to trace the light correctly. This is where the insane performance impact from ray tracing comes from. But thankfully, there is a trick which is able to make this ray tracing possible. Instead of shooting thousands of rays at a single pixel, we instead shoot just a few and try to interpolate the correct result from those. This is of course not entirely accurate and can leave artifacts on the screen, but with the correct methods and ongoing improvements to interpolation, we should eventually be able to get great accuracy in ray tracing in the future.
But why do we even go for ray tracing in the first place? The reason we strive for ray tracing is because our current rendering paradigm, rasterization, is severely limited when it comes to reflection, shadows, and transparency. But it comes at a downside. And the downside is simply put performance. It is way more computationally expensive to do ray tracing than rasterization. Thankfully, we can reduce the number of rays that we need with smart techniques, such as only throwing a few rays and then interpolating between them. This allows the upcoming graphics cards of the next generation to handle ray tracing in real time. On the downside, you might have to end up paying with a kidney for one of them, because they are quite expensive, aren't they? It is probably not worth it, but at least you'll have ray tracing before anyone else. Well, as long as the game supports it, anyways. You could also just wait for another 2 or 3 years or so until ray tracing becomes affordable to everyone. But that is a choice that you have to make now. Ray tracing or 2 functioning kidneys. Anyways, if you want to learn more about graphics and graphics cards, I can recommend you to check out my video on the grass in Ghost of Tsushima and the secret on how that was rendered. So, if you like this video, make sure to subscribe and thumbs up it. And also leave me a comment with your thoughts on the stuff presented in this video. So, I guess that's it. Thank you very much for watching, and I really hope to see you next Tuesday with my next video. So, bye!